In this video, we are going to look at loci on the Argand diagram. Now, the first thing we've got to do is we've got to know how to interpret the modulus of z minus w, where z and w are two complex numbers. So in the diagram, we've got the positions of the complex numbers z and w marked on the Argand diagram. And if we travel minus w from z, then the point at the end of the movement is going to be the point z plus minus w, in other words, z minus w. Now, the modulus of a complex number represents the length of the line joining the origin to the complex number. So the modulus of z minus w is the length of the line joining the origin to the point z minus w. So the modulus of z minus w is the length of the red line that we've got on the diagram. However, if we look at the quadrilateral formed by the origin, w, z, and z minus w, we know that the two blue sides are both parallel and equal in length. So the quadrilateral must be a parallelogram. And if it's a parallelogram, that certainly means that the two red sides must be equal in length. So the length of the line joining w to z must also be the modulus of z minus w. So the point we're trying to make on this slide is that the modulus of z minus w is the length of the line joining the point representing z to the point representing w. Okay, so we've got to now represent on the Argand diagram all the complex numbers z which satisfy the equation the modulus of z equals 3. Now we know that the modulus of z represents the distance of the point z from the origin. So we want all of the points whose distance from the origin is 3 units. So that means that z must lie on a circle of centre of the origin and radius 3 units. So there would be my sketch of all of the points that satisfy the modulus of z equals 3. Now it's worth noting that we can also attack this problem from an algebraic method. So if I've got the modulus of z equals 3 and I let z equal x plus iy, then I know that the modulus of x plus iy has got to equal 3. In other words, I know that the square root of x squared plus y squared must equal 3. Square each side, I know that x squared plus y squared must equal 9, which is the equation of a circle with centre 0, 0 and radius 3. Now in this case, I think the geometric solution is much neater, much quicker than the algebraic solution. We will find later on that sometimes we have to use the algebraic solution because the geometric solution is nowhere near as simple. Let's move on to a second example then. We want to represent on the Argand diagram all of the complex numbers z which satisfy z plus 3 minus 4i equals 3. Now I can rewrite the condition the modulus of z plus 3 minus 4i equals 3 as the modulus of z minus 3 plus 4i equals 3. And the reason I've done that is that I know that the modulus of z minus w represents the distance of z from w. So in other words, the fact that I know I want the modulus of z minus 3 plus 4i to equal 3 means that I want the point representing z to be 3 units away from the point representing minus 3 plus 4i. So I want all of the points which are 3 units away from the point minus 3 plus 4i, and that is simply going to be a circle of radius 3, and the centre has got to be the point representing minus 3 plus 4i, in other words the point minus 3, 4. So there is the locus of all of the points satisfying the modulus of z plus 3 minus 4i equals 3. Now again, that was a nice neat geometric solution. There is an algebraic solution. So if we go for the algebraic solution, we start off by letting z equal x plus iy. So the condition that I've got becomes the modulus of x plus iy plus 3 minus 4i has got to equal 3. Collect together the real terms and collect together the imaginary terms means that I've got the modulus of x plus 3 plus y minus 4 lots of I must equal 3. In other words, the square root of x plus 3 squared plus y minus 4 squared must equal 3. Square each side. I've got x plus 3 squared plus y minus 4 squared equals 9, which is exactly the equation of a circle with centre minus 3, 4 and radius 3. Our third example is slightly different. We've got to represent on the Argand diagram all of the complex numbers z which satisfy the equation the modulus of z minus 2i is the same as the modulus of z plus 2. The geometric solution says that what we have got is the modulus of z minus 2i has got to equal the modulus of z minus 2. Remember that the modulus of z minus w means the distance of z from w. So what we're saying is that the distance of z from 2i must equal the distance of z from minus 2. Now, the distance of a point from A equaling the distance of a point from B is exactly the description of the perpendicular bisector of AB. So in this case, the fact that we know that the distance of z from 2i is the same as the distance of z from minus 2 means that we know that z must be on the perpendicular bisector of the point representing 2i on the Argand diagram and the point representing minus 2 on the Argand diagram. So we can now say that means that Z is on the perpendicular bisector of the point 0, 2, which represents 2i, and the point minus 2, 0, which represents minus 2. So there's the sketch of the perpendicular bisector, and to make it quite clear in the solution that it is the perpendicular bisector of A and B, we'll put in the fact that our locus, the red line, is at right angles to AB and splits the line segment AB into two equal parts. Again, we can do this part algebraically if you don't like the geometric solution. So again, with the algebraic solution, we start off by saying let Z equal x plus iy, in which case the condition, the modulus of Z minus 2i equals the modulus of Z plus 2, becomes the modulus of x plus iy, take away 2i, equals the modulus of x plus iy plus 2. In other words, the modulus of x plus y minus 2 lots of I must equal the modulus of x plus 2 plus iy. So that's the square root of x squared plus y minus 2 squared on the left hand side must equal the square root of x plus 2 squared plus y squared on the right hand side. Square each side, we've got x squared plus y minus 2 squared must equal x plus 2 squared plus y squared. Expand the squares on each side, so we've got x squared plus y squared minus 4y plus 4 on the left hand side equals x squared plus 4x plus 4 plus y squared on the right hand side. And if we look carefully at that, we can see that the x squareds cancel on each side, the y squareds cancel on each side, and the plus 4s cancel on each side. And then if we take everything onto the right hand side, we get left with 0 equals 4x plus 4y. In other words, we've got the line x plus y equals 0, or if you like, y equals minus x. If we've done the algebraic solution, there's really no need to make it absolutely clear that that is the perpendicular bisector. Okay, we just need to make it clear that we've got the line y plus x equals 0. Now, all the examples we've looked at so far, we've had the two approaches. We've had both the geometric approach and the algebraic approach. It's up to you which one you use. I think the geometric approach is neater and quicker. There are, though, some examples where we have to use the algebraic approach, and here is one. So we've got to show on the Argand diagram all the complex numbers z which satisfy the equation the modulus of z is twice the modulus of z minus 3. Now if we try a geometric solution, the modulus of z means the distance of z from the origin, and that has got to equal twice the distance of z from 3. Making very much progress from that geometric condition requires some knowledge of something called the circle of Apollonius. And that is some fairly sort of complicated geometry kicking around there. And in this case, it's much easier for us to go down the algebraic route. So to go down the algebraic route, we're going to say, okay, let z equal x plus iy, in which case we have got the modulus of x plus iy must equal twice the modulus of x plus iy minus 3. In other words, the modulus of x plus iy has got to be equal to twice the modulus of x minus 3 plus iy. It's important we collect together the real terms and the imaginary terms before we try to calculate the modulus. So we've got the square root of x squared plus y squared must equal twice the square root of x minus 3 squared plus y squared. Now we're going to square each side to get rid of the square roots, but if we square each side we must remember to square the 2 as well. So squaring both sides, the left hand side becomes x squared plus y squared, the right hand side becomes 4 lots of x minus 3 squared plus y squared, and the 4 is the effect of squaring the 2 in the previous line. Now need to do an expansion of the brackets on the right hand side. So first of all, doing the square, we've got x squared plus y squared on the left hand side equals 4 lots of x squared minus 6x plus 9 plus y squared. In other words, x squared plus y squared equals 4x squared minus 24x plus 36 plus 4y squared, which means that we've got 0 equals 3x squared minus 24x plus 36 plus 3y squared. Got a nice factor of 3 running through that, so we may as well divide through by 3 to give 0 equals x squared minus 8x plus 12 plus y squared. If we complete the square on the x squared minus 8x, we've got x minus 4 squared take away 16. So the line above can be rewritten as 0 equals x minus 4 squared take away 16 plus 12 plus y squared. In other words, we've got 4 equals x minus 4 squared plus y squared. And that is the equation of a circle with centre 4, 0 and radius 2, which I can now draw easily on my Argand diagram. Now for our next example, we want to show on the Argand diagram all of the complex numbers z which satisfy the equation the modulus of z divided by z minus 3 equals 2. This stage it's quite important that we remember something from the previous video, and that is we know that the modulus of z over w is the same thing as the modulus of z divided by the modulus of w. So the fact that the modulus of z over z minus 3 has got to equal 2 tells me that the modulus of z divided by the modulus of z minus 3 must equal 2. In other words, the modulus of z must be twice the modulus of z minus 3. And this means that this example is actually exactly the same as the previous example that we've just worked through. So we know that the locus of z is exactly the same as it was in the previous example, namely a circle of radius 2 and centre 4, 0. Now so far all of the loci that we've been looking at have been defined in terms of modulus. Sometimes the loci will be defined in terms of argument instead of in terms of modulus. So we need to interpret arg of z minus w. Now arg of z minus w is the angle at the origin made by the line in the positive real direction and the line going off to z minus w. Now, we know that the quadrilateral formed by the origin, w, z, and z minus w is a parallelogram. So, the angle at w made by the line running parallel to the positive x direction and by the line going from w to z will have the same angle as arg of z minus w. So that means that arg of z minus w can be described as the angle at w made by a line running parallel to the positive x direction and the line going from w to z. So, we've got a series of argument loci to consider here. The first one is we've got to do the argument of z is pi by 3. In other words, the argument of z minus 0 equals pi by 3. So that means we've got the angle at 0 made by the line along the positive real axis and the line going to z must be pi by 3. So there's the line along the positive real axis, there's my angle of pi by 3, so z must lie somewhere along that half line. We call a half line a ray. So the locus of z is the ray shown on the diagram. For the second example, we've got the argument of z minus 1 plus 2i has got to equal pi by 4. So that means that it's the angle, arg of z minus 1 plus 2i is the angle at 1 plus 2i made by the line which is parallel to the positive real axis, and the line going off to z must be pi by 4. So we start by marking the point 1 plus 2i. We mark in the line parallel to the positive real axis. We know that the angle of the line going off from 1 plus 2i to z must be pi by 4. So we mark our angle in of pi by 4, and then z has to be along the ray going out from 1 plus 2i at an angle of pi by 4. And for the third example, we've got the argument of z plus 2i must be minus 2 pi by 3. Then we start by saying that means that the angle at minus 2i made by the line parallel to the positive real axis and the line going off to z must be minus 2 pi by 3. So we mark the point representing minus 2i. We put in the line through minus 2i, which is parallel to the positive real axis. We've got to make an angle of minus 2 pi by 3 with that line. Now minus 2 pi by 3 means it's got to be a clockwise angle of 2 pi by 3. And the locus of z, or z, must lie on the line going out at that angle of minus 2 pi by 3. To finish this video, there's a small exercise here, so I suggest that you pause the video at this point and work your way through as many of these examples as you can. And that now completes our work on loci on the Argand diagram.